keynote de esta sesión es Duncan Watts, que viene trabaja en la Universidad de Nueva York, es un Microsoft Research at the University of New York. Su presentación esta mañana va a ser un poco distinta de las que se han hecho hasta ahora como resumen de lo que sería el Big Data, porque diríamos que se centra en las buenas noticias del Big Data, es decir, en aquello que nos va a aportar de positivo, especialmente para la realización de las ciencias sociales. Es decir, muchas de las preguntas clásicas que se ha planteado la sociología o la ciencia política, gracias a esta gran disponibilidad de información que tenemos a través de las computadoras y a través de los sistemas de almacenaje y análisis, van a poder ser resueltas de una forma como hasta ahora no había sido posible. Él tiene un background como físico, es físico de origen. Esto puede parecer un poco extraño, que alguien que es un físico ha pasado a trabajar en las ciencias sociales, pero tampoco no es tan extraño. Algunos de los fundadores de los que serían las ciencias sociales han sido físicos, como Lazar Feld, que ha trabajado precisamente en cuestiones como la difusión de la opinión pública y han utilizado un punto de vista muchas veces parecido al de la física. Por tanto, esto no es nuevo. Lo que sí que cambia, en cambios, han sido los métodos que se pueden utilizar para realizar este análisis. Cedo la palabra a Duncan Watts, porque va a hacer una exposición que creo que es un poco larga y, por tanto, será bueno que tengamos tiempo de escucharle con detenimiento. Gracias.
I have no idea what you just said. But I hope it's okay if I speak in English because my Spanish is not very good. So thank you for having me. It's lovely to be here in Barcelona to talk to you today. So I want to talk about big data, but I want to talk about it in the context of what I do, which is social science. So I don't have to remind the people in this room that over the last 20 years we've witnessed this incredible technological revolution that we sort of refer to as the internet or the web very loosely, but by that we mean really a whole suite of digital technologies beginning with email, but then the web and cell phones and smartphones and instant messaging, social networks, microblogging. This sort of combination of all these different platforms has really sort of revolutionized a number of things in our global society. It's given us, of course, new ways to communicate with each other, and also new ways to conduct commerce, new ways to buy things. And this has led to whole new business models to provide for these new modes of consumption and communication. But along the way, it's also generated some sort of unexpected challenges to our sort of norms around privacy and who owns data. This is not really something that we even thought about 20 years ago. Intellectual property, even sort of the finer points of social etiquette have been challenged by the kinds of the language and the speed with which we can now communicate. So this is all very obvious, and people talk about it a great deal in the media and in conferences like this. But a less obvious, but in my view, equally important change that has been driven by the web is not just the changes that it's had on society, but the changes that it's had on our ability to study society. The way I think about the web is less like a printing press and more like a telescope. This is a device that makes previously invisible things visible, and so gives us the potential to do new kinds of science. So let me just say a little bit more about that and why the web is so important to social science. So when I think about, what is social? What is a sociological phenomenon? What is something that a question that sociologists would find interesting? most of the questions that sociologists study, and political scientists as well, have to do with aggregations of people. So things like political parties or firms or markets or cultures. These are, we talk about them as if they are things that can act and make decisions and have attributes and internal cultures of their own. And yet we also understand that ultimately they're really just agglomerations of individual people. And so there's something quite mysterious about this process by which you take a bunch of people and you put them together and they acquire properties that are not just those of a bunch of people, but of these sort of social and political actors. And so this is a very deep problem. It's in a way the core question of sociology, and it's called the micro-macro problem. It's what sociologists call the micro-macro problem, because somehow we go from the micro level of individuals to the macro level of social facts. And in other fields, like in physics and in complex systems, they call this emergence. So this is a very mysterious phenomenon. It happens in all the sciences, and everywhere we encounter it, it is always among the most difficult problems to understand. So why is that? Well, it's difficult from an empirical perspective, at least in the social world, for two reasons. One is that when you want to study emergence, you have to study large numbers of individuals and also their interactions and also their behaviors at scale over time. This is an enormous amount of data to collect, and historically it's been impossible. So instead we rely on things like surveys, which take samples of a population and ask people questions, but you don't actually observe them, you don't see how they interact, you can't follow them over time. There are all kinds of limitations that have constrained empirical social science for 100 years now. It's even more difficult to do experiments at large scales. You can't sort of put the proverbial army into a lab and try out different ways of forms of organization or authority or whatever in a laboratory environment and see what causes what. So, if you think about what is the scientific method that we all learned in high school, it is basically, aside from having a hypothesis, it's really all about collecting data and conducting experiments. And if you can't collect the data and you can't run the experiments, it's very hard to do science. So the reason why people like me are so excited about social science in this particular era is that some of these historical limitations are being lifted. Not all of them. I don't mean to say that the web is a panacea for social science, but it's certainly generating a scale and a scope and a granularity of data that is just sort of wildly larger and more interesting than anything that we could have even imagined 20 years ago. So this is in turn leading to sort of, I don't know if it's a field or a cluster of fields, but I'm going to refer to it very loosely as computational social science, which is the intersection of the traditional social and behavioral sciences and the computational sciences. So there's a lot of people from computer science who are now getting interested in questions that were traditionally social scientific questions from economics and political science and sociology and psychology, and they're having a huge impact simply because they're able to manage and analyze data on a scale that is very difficult for most social scientists. So to talk about computational social science, I'm really just going to talk about a couple of examples, so, two sort of types of problems that I and my colleagues have worked on over the last several years to illustrate how, in different ways, web data is changing the kinds of questions that we can ask and the kinds of questions that we can answer. And one of them is an experimental study, and one of them is an observational study, and hopefully by the end of the talk it will be clear which is which. And you'll see that when we talk about scale, what counts as big really can vary dramatically. It really depends on the question that you're asking and the method that you're using to answer the question. And I just want to sort of make a point today that as much as I'm happy that people are focusing on data and using data to evidence really to support decision making, this phrase big data bothers me a little bit because it really just emphasizes one dimension of the data, which is the scale. And sometimes, as I'll point out, the scale is really critical, right? Sometimes you actually really do need huge numbers of observations to answer very particular types of questions. Other times the scale is very uninteresting, and it's much more important how you design your research study in the first place. So the first example that I want to give you stems from a substantive problem, a puzzle in the social world that I started working on several years ago with my graduate student at the time at Columbia University, Matt Selganic, who's now a professor of sociology at Princeton University. And we were puzzled by this paradox, this combination of stylized facts that you observe when you look at cultural markets. So if we think about markets for books, for movies, for music, there's a couple of things that are very striking. One is that if you look at the most successful objects in these markets, they're not just more successful than average, they're many orders of magnitude more successful than average. So Harry Potter books have actually probably sold more like 400 million copies worldwide at this point. You know, an average book might sell a few thousand copies worldwide. So this is, or maybe even less, maybe a few hundred, right? So you have sort of most books sell very few copies, and then you get a few that sell, you know, thousands or tens of thousands of times more. And so you might, and the same is true for movies, and it's true for music, and it's true for art, it's true for all cultural markets where you see this tremendous range of inequality and success. And you might think, well, that's because the most successful things are just many times better than average things. There's lots of lousy books out there, and then you have works of genius like Harry Potter, and that's why it sold, you know, 400 million copies. And an idiot could tell you that Harry Potter is better than every other children's book ever written, and that's why it's so popular. But if an idiot could tell you that, then the 8 children's publishers who rejected J.K. Rowling's original manuscript would probably have something to say about that. Eventually, it was picked up by a very small independent press called Bloomsbury in the UK, which is now a very large independent press that is entirely, almost entirely devoted to selling Harry Potter books. So, you know, there's this problem that you have to deal with when you think, oh, it's so obvious that Harry Potter is a brilliant book. It wasn't obvious to a large number of experts in the children's publishing industry who are not only experts in children's publishing and have a lot of experience and knowledge about what children like, but are highly motivated to find the next big hit. It's not that they don't care, right? They really care, and they're really upset, these guys, that they rejected J.K. Rowling's original manuscript. And this turns out to happen all the time in these cultural markets. And it's led certain sort of cynical experts like William Goldman, writing about Hollywood, who famously said that in Hollywood nobody knows anything. And there are a number of even sort of prominent people in these fields who have said similar sorts of things. So why is this? I don't actually think that these people are idiots. I think maybe they're not as smart as they make out, but I think there are very good reasons why we see both this inequality and unpredictability, and it has to do with this macro problem, right? So that when individuals in these markets make choices about what to buy and what to like, and what to listen to, they are always and invariably influenced by what other people are doing. And maybe they do this because they think that other people know things that they don't, that other people have gone off and studied which books are good and have some experience, that, you know, they've gone and tried different restaurants, and so why not go to the popular restaurant because everyone has already figured out which ones are good. So there's a social learning explanation for why we pay attention to other people, but there's also a coordination or conformity explanation, which is that we want to read the same books that our friends are reading because then we can talk to them about them, right? So that culture in a way is about sharing common references. So from that explanation or that point of view, it doesn't necessarily matter whether one thing is better than another. The point is that we want to consume the same things. So these are actually quite different explanations, but they both have the same consequence, which is that that in the presence of social influence, markets exhibit cumulative advantage. This means that popular things have a tendency to get more popular and unpopular things have a tendency to get less popular. And you can show, in theory, quite easily that these processes, these cumulative advantage processes, generate both inequality and unpredictability. And they could explain potentially exactly the paradox that we observe in real cultural markets. The problem is that it's very hard to tell someone who is a Harry Potter fan that Harry Potter is just some sort of random accident, where everybody just started buying it because other people were buying it. And it's not actually any better than any number of other children's books, because at this point we look back in history and we're used to it being there, and we think, no, it has to be better, right? There's no other way. How could this thing be so much more successful unless it were truly better than everything else? And of course, you can't actually rule that explanation out, right? There's no way to prove that it's wrong because we only see one realization of history. History only happens once. And if we wanted to test this hypothesis, we would have to sort of go back to the mid-1990s before anyone had heard of Harry Potter and J.K. Rowling was still sitting in a coffee shop in the UK trying to write her first book. And rerun history and see if every time we rerun it, Harry Potter turns into a mega blockbuster, or if every time we rerun it, some other book turns out to be super popular and we haven't heard of J.K. Rowling. So, if Harry Potter wins every time, then we can say, well, I don't know what it is about Harry Potter, but it wins every time, so we'll say that it's got something. If a different book wins every time, then we say it's just luck, okay? Now, we can't do that in real life, which is the problem with a lot of social science, but maybe we could do it in a lab, right? Maybe we could rerun history in a lab experiment and repeat the same process many times, in a way create many different versions of the world, and we could also control how much information people have about what other people are doing. So in some worlds, we could let them be influenced by each other. In other worlds, we could force them to behave independently, and we could see whether this makes any difference. Now, there's a problem with this idea as well, which is that when you want to do an experimental design like this, in each one of these worlds, you have to have, at a bare minimum, hundreds of people, right? So then if you want to have many such worlds, you need thousands of people. And then if you want to be able to change, your experimental conditions, so you want to run one experiment and run a different version of the same experiment, then you need tens of thousands of people. And this is, far more, students than we have at Columbia University or really at any university. It's totally impossible to run experiments like this in a lab. But of course, this is back in 2004 when we started thinking about this, and this is the year that Facebook was created. And so we started to think maybe we can do this on the web. And so that's what we did. We built this website called Music Lab, and we would recruit people from online, and they would come to this page, and they have 48 grid squares on this page here, and each one is represented by a band that you've never heard of and a song. Right? So it's 48 different songs by unknown bands, and they're randomly arranged on this page, and each little square represents one of the songs, and you see there's a little number here which tells you how many times that song has been downloaded by other people. So you click on one of these squares, and the music streams through your web browser, and you can listen to it for as long as you want, give it a rating from 1 to 5 stars, and then we give you a chance to download it. And so the downloading takes a little bit of time, so there's a little bit of a cost there, and this is the action that we pay attention to. If you like it enough to download it, then we're going to say that you like it. Okay, so what you don't know when you're doing this is that you're in this funny little experimental design here, where you're arriving here and we're randomly assigning you to one of two experimental conditions. So the first one is the one I just showed you, and it's called like the social influence condition. Right? The second one is this independent condition, which looks exactly the same except there are no numbers. Right? So you have no idea who likes what. You just see the songs and the bands, and you just do whatever you do, and you have to behave in a completely independent manner. The other thing that you don't know is that if you get shunted into this social information condition, we further assign you to one of 8 different parallel worlds. And in each one of these worlds, you can only see the downloads of the people who are ahead of you in that world. So we've effectively created 9 copies of the universe, and we start everything off identically with 0 downloads, and then we just push people randomly into these conditions and see what happens. So remember, we're thinking about the micro-macro problem here. So what's happening at the micro level? Are people even paying attention to these numbers that we're giving them? And the answer is yes, they are. So here we've ranked everything from the most popular song at any point in time to the least popular song at any point in time, where market share is just the number of downloads that the song has received divided by the total number of downloads. So it's just the share of the market, literally. And so you rank everything by market share, and you can see that and the y-axis here is the probability of clicking on a song. Okay, so you can see that there's a big spike here at the end. So people are definitely noticing that some songs are more popular than others, and they're more likely to click on those songs. So this is good. There's a sanity check there. Now you might think, oh, these are just songs with cool sounding names. That could be what's going on. But if that were true, then you would see the same effect in the independent condition, and you don't. Right? If you look over here in the independent condition, there's no effect of market share on the probability of listening. Okay, so we're getting exactly the effect that we want at the micro level. Is this having any effect at the macro level? So we have to measure 2 things. Remember, we care about inequality and unpredictability. And I won't go into the details here, but we have these 2 standard measures. One is called the Gini coefficient, which measures inequality. It's frequently used in economics to study wealth inequality. And when it's 0, it goes between 0 and 1. When it's 0, all songs have exactly the same market share. When it's 1, one song has all the downloads and nobody else has anything. And the other thing that we want to measure is unpredictability, and this is a number that's also normalized between 0 and 1. So just think of it as it's the average expected difference in market share between worlds, but really just think of it as, you know, how much, if I told you what happened in one world, how much would you know about what's happening in another world? So when it's 0, each world is an exact replica of every other. So you know exactly what's happening in one world in another world if I tell you what's happening in one world. When it's 1, they're random reshufflings of each other. So you have 0 information about what's going on in another world just by knowing what happens in one. So what happens with these measures? Well, this is inequality on the left. This is unpredictability on the right. The gray bar is the independent condition. The dark bars are the social influence condition. And you can see that all the social influence worlds, all 8 of them, are more unequal than the independent world, and the social influence condition as a whole is also more unpredictable. So the direction is exactly consistent with our hypothesis that social influence is increasing both inequality and unpredictability. But you might say, well, these don't look like very big differences to me. So maybe directionally this is true, but this doesn't explain Harry Potter. And I would say, well, that's true, but the signal is also very weak. These numbers actually are kind of hard to see, and it's not easy to see which ones are the most popular. You have to sort of really stare at the screen. So we ran another version of this experiment where we we did everything exactly the same, except rather than scattering them randomly on a grid, we ordered them from most popular to least popular. So now it's much more obvious which songs are the most popular, and you can also tell smaller differences in popularity because everything's being ranked for you. This is also a much more standard way to do things online. And now you can see the signal increases, as we hope. So the open circles are the old experiment, and the solid circles are the new experiment. And you can see that there's a much bigger spike at the end, and things are dipping down in the middle, and then oddly people are actually scrolling all the way to the bottom to see what the worst songs are like. So there's a little bit of an uptick here, which probably would not happen in the real world. If we had thousands of songs, no one would scroll down to the end. So, okay, so what happens? Well, again, we see that everything gets bigger. So now you see this is experiment 1, this is experiment 2, so inequality has gone up, and unpredictability has also gone up. And so this inequality here is about a third on the Gini coefficient, and this is about the average Gini coefficient here is about 1/2. So in economic terms, this is the difference roughly between Sweden and, you know, sort of some Central African failed state, okay? So these are pretty big differences in the economic world, so that, I think, is a pretty big difference in our experiment as well. Unpredictability is also increasing quite dramatically. So another way to look at this is to rank everything in terms of how popular it is in the independent world. So we say, when people like something without knowing what other people like, we're going to say this is a measure of its intrinsic appeal. Let's call that quality. Right? And we don't want to sort of argue too much about how to define quality, but here at least we have an internally valid measure of appeal, and so we can rank everything by its appeal or its quality, its intrinsic quality, and then we can see, well, how popular is something in the social influence world as a function of its intrinsic quality, and so each song is represented by 8 dots, which are the 8 times it appears in the 8 different social influence worlds, and you can see that on average things are increasing. That the better a song is, the more popular it is on average. So this is sort of the common sense notion that better things do better. And on average, that's true, but it's a funny kind of average because it's an average over different realizations of the world. Right now, in reality, we only get one of these worlds. And so you can see that what happens in any given world is quite random. Right? There's a lot of scatter for any given song, particularly at the top end. There's a lot of variation in how well a song can do. And you can see that as we go from experiment 1 to experiment 2, the more social influence we have, the more dramatic this scattering becomes. So you can imagine in the real world, there's a lot more social influence even than we have in our little experiment. And so you could easily see how these differences can become quite enormous, even for the very, very same song. Okay. So what have I told you up till now? Individuals are clearly influenced by what others are doing, and the more information they have about what others are doing, the more they're influenced. Less intuitive is that when people know what other people like, popular things become more popular, unpopular things become less popular, and at the same time, which particular songs become popular become increasingly harder to predict. So here's the paradox, is that when you give people information about what other people like, this is real information. It's useful information, right? I mean, there's a reason why we like, you know, recommendations from friends and bestseller lists and expert opinions and reviews. It's actually helpful to us. It makes our decision-making easier. But at the same time, if we rely on the information that other people have generated, we're generating less information ourselves. So we are contributing, and at some point where we just follow the herd, we're increasing the size of the herd, but we're not adding any more information to it. So this is what economists call an information cascade, and this is effectively what we're seeing here in this experiment, is that, you know, we're giving people more information, but the market is generating less information. And if it's not obvious, this was an experiment that was superficially about music, but really it's about social influence. And I think it's easy to see how a similar kind of result could apply not just in musical markets or even cultural markets in generally, but even in financial markets, where, you know, the very concept of money is an abstract concept that is really an article of collective faith. That, you know, I believe that this piece of paper is worth 10 euros only because everybody else agrees that it's worth 10 euros. And if we stop believing that it's worth 10 euros, then it's suddenly not clear what it's worth. And that, fortunately, hasn't happened with euros yet, or US dollars, but it certainly has happened with other forms of money. And this, in fact, was really what generated the vast bulk of the last financial crisis, was that certain classes of assets that were backed by these securitized assets were thought to be worth, 100 cents in the dollar, and suddenly they became worth 20 cents in a dollar. This is a huge problem. Okay. So, moving on to the second project that I want to talk about, if you think about the lesson of Music Lab being that when social influence is present, it's impossible to predict success just knowing what the songs are. One response that we often get when we talk about this is that, okay, so maybe you can't, maybe you can't predict success as a function of the song attributes, but really what you're showing in analyzing social influence is that there are some people who are very influential, and what they like ends up being the thing that succeeds. So if you think about, in the US at least, you've probably heard of Oprah Winfrey. You may know that she had a very popular show where she talked about, she got authors on and profiled them in their books. And if you were an author, probably the best thing that could happen to you in terms of selling books is getting onto Oprah. There's a huge sort of bump that's associated with being on Oprah in book sales. So an unknown author can instantly become a bestseller. So you might think, well, this is really what's happening in these markets, is that somebody sort of decides early on that a song is good, and they promote it, and so it looks like it's random, but it's actually not random. It really depends on these influences. And so if we think about it from this point of view, if we want to predict success, then we really want to be able to identify and predict what attributes make someone an influencer. And so the question is, well, is this actually any easier than doing the thing that we just tried to do? And so this is another problem that we've worked on over the years, and this is tricky because now you need to really be able to see who influences whom, and this is a hard problem to do. This is a hard observational problem to solve in the world, because you've got large numbers of people and everyone's kind of communicating with each other, and it's really sort of hard to track who's paying attention to whom, and whether they're actually responding to that information. We could sort of do it in a very simplified way in Music Lab, but that's very unrealistic. There was no network in Music Lab. There were people just sort of arriving in a queue. And in the real world, we know that people talk to each other and they have conversations, and information kind of flows through these networks. So we really need to study this in a network setting. And right around, this was back in 2009 when we started this project, and then that was a time when Twitter was really just starting to get very big and had a couple of 100 million people using it. And it occurred to us that Twitter is actually a really great place to study influences, because you have a network which, unlike other kinds of networks like, say, for example, Facebook, where people are friends with each other on Facebook for all sorts of reasons. So it's totally unclear. If you see two people linked on Facebook, you don't necessarily know why. On Twitter, there's really only one reason to follow someone, because you want to hear what they have to say. Okay? They're not necessarily your friend. They're just saying stuff, and you want to listen. And the only reason to tweet on Twitter is because you want people to pay attention to you. So this is a sort of a network that is all about people trying to influence each other, at least in the sort of very limited sense of paying attention and possibly retweeting or passing along a piece of information. So we also, another nice feature of Twitter is that a lot of what people put on Twitter when they're not talking about what they're having for lunch or sending photos of their surroundings, they're actually taking content from other places online and they're putting it into a tweet in the form of a URL. Right? So when these things get shortened, these URLs get shortened, and so we effectively have a unique tag, a code, that tells us exactly what piece of content this is. And so we can see individual pieces of content flowing around this enormous network, and there are now billions of pieces of content flowing around this network, and all of this can be tracked. Okay, so this is a sort of really phenomenal advance in terms of observing information flows in a real ecology. And so we did this back in 2009, and we took about 1 billion total posts, and then we just took the relatively small subset of 74 million such posts that contain bit.ly URLs. Bit.ly used to be the most popular URL shortener until Twitter effectively killed it by introducing their own Now it's all t.co, but back then it was bit.ly. So we have about 1.6 million users who have introduced at least one bit.ly URL over this 2-month period, and so we can, and we also have all the links between them. So we want to compute how influential each one of these users is. And the way we do that is we treat them as a seed node. So we take a person and they introduce a new piece of content that no one else has, at least they've introduced it independently. And then every time somebody retweets that piece of content, that exact same piece of content, whether it's one of their followers or one of their followers' followers, then we give that seed node a point. We say it has 1 point of influence. And then we repeat this process for every time they introduce a new piece of content. And so over time, we can average all of these numbers, and we can give this person an influence score. Okay. So this, in some ways, is a funny measure because we insist that people retweet stuff, and there's a lot of, you may read something, you may click on something, you may be influenced by it and never actually retweet it. We're not going to see that. But we also, we wanted to be as strict as we could. At least when you retweet something, we know that you have been influenced by it. Okay. So this is sort of some of the pictures that you see, and I'll show you some more pictures later. You get all kinds of structures for these cascades. So each one of these, the way to read these pictures is that the node at the top is the one that introduces it, and everybody else is retweeting that same piece of content. And some of these things are broad and flat, and some of them are narrow and deep. Some of them are very small. Actually, most of them will turn out to be very small. And some of them are very sort of interesting and complicated. So what we want to do is, given everything that we can measure about this initial person, can we predict how big this cascade is going to be? That's all we're trying to do. And we know a lot about them. We know how many followers they have, how many people they follow, how many of those ties are reciprocated, how much tweeting they've done, when they joined. We can also do something that's really only possible on Twitter, which is to take 2 months of this data, and then we split it in half. And then we imagine that we're in the midpoint, that we have the first month of data, but we don't yet have the second month of data. And so we train our model, our statistical model, on the first month of data. And then we make predictions about how influential you're going to be in the second month. And then we evaluate our model on, as we get this new data that we pretend we don't have, we can then evaluate our model. And so we also know how influential you were during the first month. And so this is a lot of information to have, but it's exactly what you would do if you were trying to predict information on Twitter. Okay? So it turns out that of all the things that we looked at, and we even looked at some of the content that people were tweeting, and we got people to code the content and say whether it was interesting or uninteresting or something that they were likely to retweet. So we have a lot of information about the content and also about the people starting it. And the only things that matter in terms of prediction are how influential you were last month and how many followers you have. So just 2 variables get you everything that you're going to get. And you can see that, here's the predicted influence on the x-axis, and here's the actual influence on the y-axis, and the dots represent the average, and you can see that this average lies along the diagonal, and so this actually is pretty good on average, right? So you can say, oh, we're predicting influence, that's great. But then you look at all these bars here, and these represent the variance around the average, and you can see, in fact, that there's a lot of random scatter. So in any given instance, you can be anywhere along this bar here, right? So this is actually a very similar result to the Music Lab result, right? That you, on average, people who, we have this model that says this is how influential you're going to be on average. It's related to what's going on in reality, but in any given instance, there's a huge amount of variation. Okay, so what's driving this? Really what's driving it is that Twitter is sort of surprisingly boring on average, okay? So you sort of think of people talk about stuff going viral online and on Twitter, and we sort of imagine these enormous cascades. It turns out that over 90% of the time, this is what happens. I introduce a piece of content and nobody pays attention. Maybe you have experienced this. And then about 8% of the time, one person retweets it. And about 1% of the time, 2 of your followers retweet it. And 1% of the time, something else happens. Okay? So 99% of all events look like one of these three things here. So most of what's happening on Twitter is very simple and very boring. And so everything else, everything that we talk about is packed into this tiny little bar here. And so you might think, well, Twitter is just strange. Of course, this is what our colleagues told us after we told them the result. They said, oh, well, that's just Twitter. You know, nothing really happens on Twitter. That's actually not true, but it is true most of the time. So we said, okay, let's go get a bunch of other examples. So we got 5 other different projects that we had worked on, or our colleagues had worked on, and I won't go into the details here, but they're very different. They're very different networks. They're very different definitions of adoption. You know, there's very different motivations associated with why you might want to adopt the content that's spreading on these networks. So we tried to find the most diverse set of things that we could, and we find really remarkably similar patterns across all of these different examples. So the Twitter example is on the top right here. So these are the 3 things I showed you. There are 2 other little structures that appear with very, very low probabilities, like 0.3% of this, 0.3% looks like this. And everything else looks almost exactly the same. There are actually only, so each one of these we call a motif. There's 5 possible motifs for each of 6 projects. So there's 30 different possibilities that you might find, and we only see 7. Right? So basically everything looks like this, and then sometimes you see this, and sometimes you see this. And that's pretty much all that happens. So you could explain a lot about the world with a very, very simple model, and it wouldn't have any sort of interesting behavior at all. Okay, well, I mean, that's interesting in itself, I think. Okay, so what's going on here? I mean, we do see these large cascades occasionally. They're extremely rare, and I'll show you a little bit more about that in a second. And when we see something big and interesting, we want to explain it. We want to build a model that says, okay, why are rich people rich? Why are successful companies successful? Why are viral videos viral? And so we look at a few examples, and we think we see a few things in common, and we say, okay, here's the pattern. This explains what we're observing in the world. But what we don't know when we do that is that there's a huge, vast mountain of other things that are going on in this very same system, and many of those things that we're not looking at, that are not successful and are not interesting, have exactly the same features as the successful things, right? So just because successful things share certain attributes doesn't mean that those attributes are predictive of success. And this turns out to be a very common problem in the social sciences when we're dealing with rare events, whether it's school shootings or plane crashes or terrorist attacks. We always are able to sort of tell some story after the fact about, this happened and this happened and this happened, and that's why it happened, right? And then we think every time that sequence of things happens is going to lead to the same outcome. And in fact, the vast majority of the time, it doesn't. Okay, so there's a big difference between being able to explain things or make sense of things after the fact and be able to predict them in the future. And of course, it's really the prediction that we care about. No matter what we tell ourselves, the only reason we tell stories about best-selling books and viral videos is because we somehow think that we might be able to anticipate the next one. So what are marketers supposed to do? Well, rely less on stories and less on being able to sort of make predictions about individual events, and instead try to think more stochastically, to think more in terms of random processes and averages and many, many, many attempts. So it is possible to improve your average performance by 10 or 20%, and if you can do that 1,000 or 1,000,000 times, that's actually really great. That's a fantastic business model. But it just involves a very different way of thinking. It also changes how you think about influences. I mean, I've spent many years talking to marketers who are just insistent that they want to find the influencers and influence them. Just tell me who the influencers are. I want the key influencers. I want to change, I want people to buy my product. I want people to adopt better health practices. I want people to, I want to change the culture of my organization. Where are the key influencers, right? Let's go talk to them. This is just the wrong question, okay? Because the question assumes two things that are not true, right? It assumes that some people are influential and other people aren't, right? That there's this dichotomy in the world. And second, that this distinction is stable across context and time, right? That whatever it is that I'm trying to do, here are the influences. And the reality is that everyone is actually influential to some degree some of the time, right? So there's always this continuum, and this continuum constantly changes, right? That depending on very sort of subtle differences in timing and context, right? So it may still be true that some people like Oprah, I would get my book on Oprah if I could. That would be it would be stupid not to do that, because on average, she is a lot more influential in terms of getting people to buy books. But she's also very expensive, right? It's very difficult to get on Oprah. There are very few slots. Unless you have some special access, it probably costs you a lot of money, or you have to be extremely lucky. And so you have to weigh that against the benefits, that you just have to sort of think in terms of costs and benefits, and think of running many repeated experiments. And this is not as sexy as finding the influences and reaching your tipping point. But this, I think, is actually how social change happens. And the sooner we recognize that, then the sooner we'll be able to act productively. And so you may say, okay, that's fine, but I don't care about any of that. I really care about this. Does everyone know what this is? Does anyone not know what this is? Okay, good. This video has over 1 billion downloads on YouTube, right? Maybe it's 2 billion now. Like, 1 in 4 people on the planet have watched this video. I have no idea why this video is so popular, okay? Anyone who tries to explain why this video is so popular is lying, okay? I think it's very funny and amusing, but I just, if you'd shown this to like 1,000 well-informed people like 2 years ago and said, is this going to be the most viewed video on the planet? I'm pretty sure they all would have said no. Okay, so we know that these things happen. These really, really big things. And I'm talking about all these really small things. And you may say, fine, you're missing something. You're obviously missing something. And it's true. I am missing something. And I'll explain in a moment why. But when you hear about videos like this, we say that things go viral. But we don't actually really know what we mean by that. We probably think we mean something like this. This is what a virus looks like when a virus spreads through a population, that you have starts with one person, and then they give it to a few people, and then they give it to a few people, and you have this sort of massive branching structure that grows exponentially fast over time. And this is what viral means in the biological sphere, and we've just sort of imported this term into the social media world, and it probably means something like that. But actually what could be going on is this, right? That, if this video gets on the front page of Yahoo, 100 million people see it, and they all watch it, that's just sort of a massive ball. It's like, millions or tens of millions of people watch the final of the European Cup. Nobody thinks that's viral, okay? That's a broadcast event. So it could be that big popular things that we know about spread like broadcasts, or it could be that they spread like viruses, and we don't really know, right? We just know that something is popular. We don't know how it got popular. So we decided to investigate this as well. And this is a project that we're still finishing up. So we went back to Twitter again, and last time we had 2 months of data, and we didn't see any of these big events, right, in this data. but maybe we just didn't look enough, right? So now we get 12 months of data. And in 12 months of data, we have everything. Every video, every news story, every image, every petition. It's several billion observations in total. We then say we only want to look at the popular things. So all that stuff that I just showed you, we're going to throw all of that out. We're only going to look at things that get at least 100 adoptions, right? So at least 100 people have retweeted this content. So now we are exclusively looking at popular stuff. And so now we go from a few billion to 350,000. So this is sort of this is like roughly 1 in 10,000. So we're already looking at very, very rare events. But because we have such an enormous population to begin with, of billions of events, we still have hundreds of thousands of these very rare events, okay? So this is, again, something that just would have been inconceivable even a few years ago when you couldn't collect that data. And so now we can ask, well, let's just look at these popular things. Are they typically like broadcasts, or are they typically viral? Or is there some sort of, magic combination of the two that generates popularity? And so, come up with your own pet theory. It's going to be wrong, because we actually see everything, right? We see every kind of, if you just condition on a given level of popularity, all of these pictures here have the same, or roughly the same number of total adoptions, right? The one on the top left here is where I think it's a CNN story. So this is CNN broadcast this story, a whole bunch of people who follow CNN retweet it, and nobody else touches it, okay? But a lot of people retweet it. And then I think this is some obituary in the New York Times that was about this crazy French guy who was a freedom fighter in World War II and led the most interesting life you could possibly imagine. And his obit was just a fantastic story, and people started sharing it, and it spread like this. So this thing looks very, very viral, and this thing looks very much like a broadcast. And in fact, we see both of those structures, and we see everything in between. So we see stuff that has kind of mixtures of broadcasts. So we see some things that have a few broadcasts, some things that have many broadcasts and a little bit of virality, and then you see more and more and more virality. All of this is present, right? So there is no sort of typical way in which things happen. They happen in every which way. We see this across all the domains that we look at. It actually isn't the case that video and news and images spread differently. You might think that they do, but they all exhibit this same pattern. Interestingly, petitions are a bit different. Petitions for a given size tend to be more viral. And you can tell a story about that they don't have media to promote them, so if it's going to be big, it has to be spread by word of mouth. But it's very easy to tell that after we know the answer. We also, again, we see very little correlation between size and virality. So, at any size, we see a lot of variation in terms of virality. So just telling you how big something is tells you very little about how it got that way. And at least so far, much of this seems to be driven by this extreme heterogeneity that we see on Twitter, that most people have a few hundred followers at most, or a few hundred followers, and then you have people like Justin Bieber, who has 35 million followers roughly, and is followed by every single teenage girl in the US and probably the whole world. And so, he's like a TV station. I mean, 35 million there are very, very few network shows on television in the US anymore that have 35 million viewers. I mean, the Super Bowl gets about 80 million viewers. So Justin Bieber is like a media station at this point, which is a little frightening. So you sort of, all this stuff is just kind of dying out, but then it hits one of these big hubs and gets a lease of life. And I think that's why we see this crazy variability. So what do we learn here about big data? Well, this is an example where the big part of the data really, really matters. Like, you just could not do this with 1,000 observations or 100,000 observations or even 100 million observations, right? You need these events are so rare, and we literally see things that are 1 in a billion events. These are things that just should not happen in theory, right? and they almost don't happen. But even, you know, at 1 in a billion, like, you know, it's sort of, anything that's not impossible can happen, right? And so you really can start to study phenomena that would have just been impossible to even think about until you had this kind of data. And in fact, we're even getting new theoretical insights out of this empirical study, that there's this long literature that I haven't talked about today on mathematical models of disease spreading, and this is really sort of giving us a new perspective on this theoretical literature. So this is, I would say, a nice example of what we call computational social science, because it's a, you know, it's an old standing question, but it really has computational aspects. But, you know, I also want to point out the limitations of big data, that you know, this is an example of where it really helps, and there are other examples as well, like in studying advertising effectiveness. You have to tease out very, very small effects from display advertising, so you need very, very large samples to be able to do it. But the music lab example is not really big. This is not 1 billion observations. This is 30,000. You can put this in a spreadsheet, right? This is not, you know, not a huge amount of data. It's certainly large by the standards of experimental social science, but that's because, you know, traditionally people would, you know, you would study sort of a few dozen subjects, or maybe 100 subjects. So it's large, but it's not web scale data. And yet we are able to get a type of insight out of Music Lab that you would not be able to get from scraping, you know, billions of observations off Twitter. You cannot get causal inference out of observational data, but you can get it when you run the right kind of experiment. So I guess the point that I would leave you with is that if we sort of, we can be happy about big data, but I'm more interested in the big problems that we have to solve as social scientists. And I'm certainly excited about the new types of data that are being driven or generated by the web, but it's certainly going to require more than just getting more of this data. We're also going to have to think very creatively about designing the right experiments and about connecting these experiments with other kinds of studies, like observational studies as well. So thank you very much. Do you have any?
Tenemos 5 minutos, 5 minutes.
Sure.
Questions?
Thank you very much for your presentation, really interesting. Well, in my case, when I listen, that it's really difficult or almost impossible to predict emergency processes. Well, obviously I agree with all your explanation, but for instance, in terms of, maybe it's my bias, of political consequences, when it is impossible to predict a specific event with political consequences, like, for instance, an economical crisis. In your case, you can find patterns, maybe not to make a very accurate prediction, but to kind of say, well, we are really near to an economical crisis, and also to sign political responsibilities. I don't know.
So, okay, so that's a good question. I think so. I think we certainly there's a difference here between the kinds of, I think the distinction I would like to make is between the kinds of things that we can make predictions about and the kinds of things that we would like to make predictions about, right? So I do think it's possible to make predictions in the same way that it's possible to make predictions about what cards are going to come up in a game of poker, right? Or you know what or you know what's going to, you know, what the die is going to roll, right? Even totally sort of random processes, you can make predictions about probabilities, right? Some things are more likely than others, right? And if you count cards in poker, right, and you're very good at it, and you're very good at computing probabilities, then on average you can win, right? You can do very well, and people play sort of, you know, people use statistical models to win at poker, right? But they acknowledge that any given, you know, turn of the card is a random event. Right? They can't predict deterministically what is going to happen next, but they can predict that certain things are more likely to happen than others. Okay? And this is the kind of prediction that I think we can make, right? And so it may be true that, you know, we can look for factors that are sort of predictive of, you know, whether we use, you know, theoretical models or we use, you know, historical evidence, that we can look for factors that are more predictive of an impending financial crisis, like, you know, credit bubbles is one sort of thing that is very commonly associated with financial crises. But there's a limit, right? So you can predict probabilities maybe, but you can't predict when actual events, right? You cannot predict, you know, the timing of a market crash. You cannot predict the particular outcome that is going to be realized. And unfortunately, that's really what we want to do, right? We always want that, right? We might, you know, you can sort of use all the statistical modeling that you like, but at the end of the day, we don't care about the sort of envelope of possibilities. We care about what is the thing that is going to happen. Is it going to rain tomorrow or not? Tell me, right? Because then I know whether to take my umbrella. What is this 40% probability rubbish, you know? And, you know, weather forecasting is actually very well calibrated. Like when, you know, 40% of the days when they say there's a 40% chance of rain, it rains, right? This is the best we can do, okay? But people always complain about weather forecasting, right? It's not because it's not well calibrated, it's because they want something else. And this is the problem that we have to wrap our heads around, is we have to stop wanting the thing that we can't have and instead focus on what we can have, which is, you know, at best, probabilistic models. Yeah.
Thank you. That was very interesting. And it's an enormous relief, of course, that this prediction is not as precise as some people think, because to the extent that you can predict from big data, those who have big data can manipulate, especially if others don't have it. What interests me is how you see the relationship of what you're doing. You're speaking about prediction, statistical inferencing, to the term causality and the term explanation. When you look at social science, there is a term explanation used in the sense of causal, causal explanation or understanding. So you look at reasons, and especially if you're talking about people, you use this wonderful metaphor of the telescope instead of the printing press. The printing press is about people, about intention. The telescope looks at things. So what you're doing with big data is you're looking at people as things. How would you relate statistical inferencing to causality and understanding? So to reasons, intentions, causality. I heard you say several times, sorry, I heard you say several times that you're inferencing causality, but you're basically inferencing a direction of a correlation. And I wouldn't want to say scientifically that that is a causation. You can look at genes, for instance, and have a correlation with disease, and you can have the direction of the correlation, but you know nothing about causality.
No, absolutely. So there's several really nice questions in there. I'll try to remember them all. So there's you're absolutely right. There's a very big difference between being able to predict and having an understanding of causality, which is sort of what we think we mean when we say an explanation. So sometimes prediction is fine. Sometimes all you care about is making a good prediction, and you don't actually even necessarily care about causality. And so as long as we're in that regime, then, you know, if we can make good, you know, we can use this observational data and we can make predictions, and there's huge business models that are associated with doing that, right? You know, the machine learning algorithms that are used to predict, you know, prices for display ads, they have like 1 million parameters in them. They don't even show you the covariates because it just makes no sense, right? All that matters is that it works, okay? Now, for a social scientist, you say, well, that's unsatisfying to me. I want to have a causal explanation. And I often also want to have causal explanations. But we have to be careful because a lot of explanations that look like causal explanations in the social sciences are actually not, right? They are, you know, effectively stories that are descriptions of one thing that happened, and then we kind of tack on a plausible mechanism, but we are unable to, we can't, in order for it to be, certainly in order for it to be predictive, it doesn't have to be causal, but in order for it to be causal, it does have to be predictive in a certain sense. And people get very cross with me when I say this because they say, no, 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 what about, you know, Darwinian evolution, right? This is a incredibly powerful explanatory theory, but it doesn't make predictions. But it does make predictions, right? It just doesn't make predictions of the kind that I just described. It doesn't predict what a mouse is going to look like in 10,000 years from now, but it did predict that there was a gap in the fossil records, right? And that prediction turned out to be right, okay? So it does make predictions about sort of statistical distributions of things, right? It makes predictions about the relationships between certain things and other things. And so I think for a theory to really be powerful and causal, it has to make those kinds of predictions. And I think that a lot of so-called causal explanations in the social sciences do not stand up to that test. So as far as what I was talking about when I talk about causal inference, I don't make that claim for the second half of the talk, right? The Twitter stuff, that is observational data. All we're doing there is making predictions. Yes, you know, sometimes we tell stories that sound like causal explanations. I hope I try not to fall for that mistake, but I probably do. But I do claim causality for the music lab, right? And the reason is that that is an experiment, right? That is where we are randomly assigning people to different conditions. That is not just a statistical correlation. That is as good as you get to causality. That you are manipulating one thing, and you're getting different outcomes across treatments. And if that's not causality, then we have no hope of.
Well,
that is the gold standard.
You have no idea of the causal chain, of course. That's what I mean. You have a correlation with a direction. That's something else. I would say then, in a scientific sense, causality. It's like if you have a specific gene that correlates with Huntington disease, that's a correlation with the direction. But to have the causal chain, which medical scientists might be interested in, is to look at exactly how the DNA codes the RNA, how it goes on. So for marketing, of course, you're not interested in science. You're interested in your business models. But to call it social science is perhaps, let's say, too early. Because the framing of the questions is based on what you can do with the big data, and that is correlation. You're also not interested, I think, and I don't mean you personally, but
well, so at some point everything is a correlation, then, right?
Absolutely. Yes, of course.
That we could. You're absolutely right that I maintain that we can say that social influence is causing inequality and unpredictability. You're correct that we can't say how, right? We do not have the whole causal chain, right? And then you could say, okay, well, let's run another whole bunch of experiments where we try to, you know, is it information? Is it coordination? What's going on in the brain? You know, we could sort of run a whole series of experiments where we try to kind of, you know, break that causal chain down into pieces. But, you know, then at the end of the day, you have the same problem, which is that you always just have a, you know, an effect size.
If you frame it that way, yes. But if you frame it in terms of the content, you get an entirely different question. But
well, so I suspect that you like theories, right? So if I had a theory,
it depends on what you mean with theory.
I mean, I like theories too, but and I agree that there's a very powerful complementarity between theory and experiment, which has been very successful in the natural sciences, of course. But just because you have a theory doesn't mean that you have causality either, right? You know, that's just a story. until you have the evidence to support it. So we have a lot of theories in social science, okay, and very little data, and very little in the way of experiments. So I absolutely agree that theories are essential to, designing experiments and to knowing how to interpret the answers that you find. But, if you sort of think of the balance in terms of like, well, how much do we have in terms of, data and evidence, and how much do we have in terms of theory? We're very theory heavy right now. So a little bit of rebalancing the balance wouldn't be bad for social science, I think.